algorithm as well as extend the algorithms and prove the approximation ratio for our problem. So the CAD mission algorithm basically accepts the job from the machine earliest finish time first, and the criterion is to consider the job only if the W is the total weight of all scheduled jobs overlapping with the current job. We'll accept the job J if the weight of the job is greater than the sum of all the jobs overlapping with it times some constant. So we can easily extend this algorithm for the machine plus the rate-dependent time windows. And the approximation ratio still holds. And we can also extend this for the centralized online global admission algorithm, where we consider not just machine by machine, but with all machines at the same time by the earliest finish time. Whereas the two-phase algorithm, where it improves the approximation ratio, it works in two phases. In the first phase, it pushes the candidates on the stack, and then in the second phase, it pops the elements, the jobs from the stack and schedules the intervals according to certain criteria. And this we can also extend easily to the machine plus rate and dependent windows, and the approximation still holds. But we can also extend the same algorithm to the machine plus rate and the power dependent time windows. The approximation ratio is going to be, of course, slightly higher. It's 2 plus the I, where I is the maximum number of overlapping machines at a given time. So the first algorithm is we can enumerate all the jobs with different combinations of the job, machine, and a row, which is the rate, with any starting time. And we can run the CAD mission algorithm. The approximation ratio still holds as 3 plus 2 squared of 2. But for the online case, where the jobs can come and go, in the online case, we consider that if the job comes, before the job comes, nothing is known. But when the job comes, everything becomes known. We can, since the rates introduce a lot of instances that we can consider, we can pre-select a particular rate where we pick the rate with the maximum ratio of the contact window over the job size. And then we can use run the same CAD mission algorithm. Of course, the approximation guarantee is going to is not going to hold in this case. So the two-phase algorithm we can also extend, as I spoke earlier, but we can also extend it for the with the power control and with the rate selection with the approximation guarantee of 2 plus I. How much do you have? Okay, so for the simulation settings, we consider the discrete rate levels and discrete power levels, and we consider different separation between the access points, and we vary them. And we use the random waypoint model for the parts of different speeds. What's the random waypoint? We can start a car at a particular location and pick a particular end location, and then depending on the speed, we'll simulate the movement of the car, and this will give us the contact windows for the car. So the contact windows are calculated using the Shannon's formula, and the data size are uniformly distributed regarding the interval. The weights are also distributed, and the interference matrix is going to be calculated in our simulation using the protocol model. So I'll just show you some of the simulation results. Now for the we can separately study the power control or the rate control. So if you consider only one base station, it's always optimal to consider the highest power. Now, is it always optimal to consider the highest rate for each machine? And then this is not necessarily. Or is it always optimal to consider highest, lowest rate? Not necessarily. As you see for the picture, as you see, we run the IP for the rate control with one AP. For the maximum rate, this is the throughput we get. For the minimum rate, this is the throughput we get. But with the optimal, with all the rates, is this line. Well, it's actually more optimal to just pre-select the rate, which relates to the max ratio, which is this. And it actually is useful for the for the centralized online case. So I'm going to skip those two experiments and I'll go to the last two. For the power control and the rate selection, for the long base station, the maximum power always gives the optimal solution. So we get this. And for the mean power, we get this line. Now, if you, what's the minimum? Since the minimum power gives you smaller contact windows, it makes it harder to schedule the job. But with our algorithm, we get the highest high throughput than by employing just the minimum power. Now, for the last experiment that I'm going to demonstrate here, this is an experiment for the 3 access points which are located on a line, and a convoy of cars moving from along a particular line, Now, of course, applying the maximum power is not necessarily going to give you a maximum throughput, but it is a near optimal by applying the max power, which is this one, because of the interference. Whereas the mean power, we pick the parameters such that no interference happens. Now, as happens that our algorithm for the two-phase power control, it outperforms the one that doesn't create any interference. So even though you have some interference, it may still have some positive it may have some positive things, even if you do have the interference, but you can still schedule the jobs within particular contact windows. And with that, I'm going to conclude, and I will go through the questions.
We have time for one quick question. So I have one quick one. On the previous slide that you were just showing us, so you said your two-phase approach outperforms IP min power. Any intuition why it doesn't achieve the same total weight as IP max power?
The IP max power, it is not the optimal solution because you still have the interference there, but it's near optimal, and I would not do I would not give any indication to the
Any other questions? Then with that, let's thank your speaker one more time. So that concludes the first session of the program. Lunch is served right outside. If you go to the left, there's a buffet there. You can help yourselves and sit down and enjoy. And we'll try to resume. Let's see what time. So we'll start in 1 hour.